All right, let's dive into one of the biggest cosmic detective stories out there, the case of the missing antimatter. And this isn't just some abstract puzzle, it's a mystery about our very own existence. Because if you really look at our best theories of physics, you, me, and literally everything you can see, well, we just shouldn't be here. Right from the get-go, we run into this massive paradox. Our understanding of the Big Bang says it should have created matter and its perfect twin, antimatter, in exactly equal amounts. Now the problem is, whenever matter and antimatter meet, they annihilate each other in a flash of pure energy. So the universe should be nothing but a vast, empty sea of light. And yet, well, look around. Here we are. The very fact that we exist means that somewhere along the line, that perfect, balanced picture went wonderfully wrong. Our existence wasn't a given. It's actually the result of some fundamental cosmic glitch. So our mission today is to play detective and figure out how the universe tipped the scales in favor of matter. To really understand the crime, we first have to understand the rules that were supposed to be in place. So let's head all the way back to the very first moments of the universe and look at the fundamental principles that should have been running the whole show. Okay, so the biggest rule in the cosmic playbook is something called CPT symmetry. It's a cornerstone of physics, and it basically says the universe doesn't play favorites. If you take any interaction between particles and you swap them for their antiparticles, look at a mirror image, and run time backward, the laws of physics have to work exactly the same way. No exceptions.
And because of that deep symmetry, the Big Bang should have been perfectly fair. For every single quark, there should have been an antiquark. For every electron, a positron. A perfectly balanced universe, destined to completely annihilate itself, leaving behind nothing but a quiet glow of photons.
But of course, that's not what happened, is it? By observing the cosmos, we've found the crucial clue. The smoking gun that tells us those rules were broken. It's an imbalance so incredibly tiny it's almost hard to believe, but it's the reason for everything.
And this is where it gets absolutely wild. The theory predicted a perfect one-to-one matchup, right? A billion matter particles for every billion antimatter particles. But what we found is that for every billion antimatter particles, the universe seems to have made 1,000,000,001 matter particles. Just one extra. After all the annihilation was over, that tiny 1 in a billion fraction was all that was left. And that remainder, that's the entire universe we know. That's us.
Physicists have actually put a number on this. This is it. It's called the baryon to photon ratio. It's the hard observational evidence comparing the amount of leftover matter to the photons created in the annihilation. This isn't just a theory, it's a measurement. It's the tiny number that proves our universe isn't empty. It's the reason we exist.
So let this sink in for a second. Every single atom in your body, in the planet, in every star and galaxy you've ever seen, it's all just the leftover stuff. We are the survivors of an ancient cosmic war, here only because of a tiny 1 in a billion head start.
Okay, so we've established a crime was committed. We've got the evidence of the leftovers. So how do we find the culprit? Well, back in 1967, a brilliant physicist named Andrei Sakharov gave us a checklist, 3 conditions that any theory absolutely must meet to explain how this all happened.
And these are the famous Sakharov conditions. First, you need a way to actually create more matter than antimatter. That's called baryon number violation. Second, the laws of physics themselves have to be biased. They have to treat matter and antimatter just a little bit differently. That's C and CP violation. And third, this all needs to happen during the chaotic, rapidly expanding mess of the early universe, when things were out of thermal equilibrium. Any theory that wants to solve this mystery has to tick all 3 of these boxes.
So, with our checklist in hand, it's time to bring in our prime suspect, the standard model of particle physics. I mean, this is our best, most rigorously tested theory of how particles and forces work. Surely it has what it takes to explain our existence, right? And you know, at first glance, the standard model looks pretty good for it. It actually has hints of all 3 Sakharov conditions baked right into its mathematics. It seems to have the motive, the means, and the opportunity. So, case closed? Well, not quite. Because when we really look at the scorecard, the standard model falls way short. Yes, it has some CP violation, but the effect is millions of times too weak to do the job. Sure, it allows for baryon number violation, but only at insanely high temperatures. And its mechanism for going out of equilibrium is just too mild. So while the standard model technically checks the boxes on paper, in reality,
The effects it produces are nowhere near powerful enough to create the universe we live in.
And this right here is the heart of the problem. Our main suspect, the theory that describes almost everything else with stunning precision, has a solid alibi. It just couldn't have pulled this off. But you know what? That isn't a failure. It's an incredible clue. It tells us with almost total certainty that there must be new physics out there, beyond what we currently know. And this is where the detective story gets really exciting. Because now, physicists are chasing down a whole new set of leads, looking for new particles and new forces that could finally crack this case wide open.
A few leading ideas are on the table. One is called leptogenesis, which suggests the imbalance actually started with lighter particles like neutrinos, and then got transferred over to the matter we're made of. Then you have grand unified theories, or GUTS, which imagine a time when all the forces were one, opening up new ways to create matter. And other ideas suggest there are undiscovered particles that could have amped up the whole process. These aren't just ideas, they're the things experiments at places like the Large Hadron Collider are actively hunting for right now. When you take a step back, you realize this isn't just some particle physics puzzle. This 1 in a billion glitch is a kind of cosmic fine-tuning for existence itself. If that imbalance had been any different, or hadn't been there at all, there'd be no stable atoms, no chemistry, no galaxies, no stars, no planets, and certainly no one around to wonder about it.
And that leaves us with this final, mind-bending question. When we finally solve this case, what are we going to find? Will we discover that the universe has a fundamental preference, a kind of built-in handedness that just favors matter over its reflection? Solving the case of the missing antimatter won't just tell us why we're here. It might just reveal one of the deepest, most fundamental truths about the nature of reality itself.